All right, welcome back, folks. Happy New Year's Eve. Um, I'd like to go ahead. So no questions still on. I don't from emails. So um, and a few more of you are starting to watch the videos, but please, please, you guys, you got to make sure you watch these videos. Don't try to cram them in and binge them all in a couple sittings. Okay. All right. So let me go ahead. I got to plug in my whiteboard here, and let me go ahead and start the timer. That way I don't run over time. But let me go ahead then. Let's quickly review where we left off with yesterday. And what I hope then that you were able to kind of follow along with the discussion that we had yesterday. Essentially, I've noticed in the past, it's the conceptual problems, the problems that involves not so much the calculations, or the calculations end up being very simple, but the problems that involve understanding the concepts that you have to apply to understanding equilibrium and how of acids and bases, and how that equilibrium can be interpreted and what we can do with that interpretation. So essentially, the conceptual questions that are asked of students. Those are the ones that they have students have the most problems with on the AP exam. And so what I'd like to do then is I want to continue on with the one more problem that involves using Ka to answer some question about equilibrium, okay, about equilibrium involving acids and their conjugate bases. So I would highly suggest that you practice those problems. Again, like I said, in the past, the issue was not so much calculating for Ka or calculating for pH, which we will do in just a moment. I'm going to suggest that you do set C. So please make sure you get set C done from chapter 14. That'll help you with the work that we calculated for the Ka. That'll help you with doing the pH, which we'll talk about. But like I said, from my experience, the calculations that we will be doing involving acid equilibrium, those are very straightforward. They will be the ICE tables again, which we learned back in chapter 13, applying the 5% rule. Those problems are easily learned. You folks in the past, my students in the past, have done well with those types of problems, and most students do. It's these problems here, these conceptual problems, the ones that we went over yesterday, that I think if you can grasp and understand how we came to those answers, if you're able to understand the explanations that I gave you, um, then first of all, you have a very good grasp of what the acid equilibrium is all about. And secondly, you'll be able to do those calculations very easily. Okay. All right. So let me go ahead then and let me share with you. Let's go ahead then. Let's take a look at number 7 in your problem set. Let's do number 7 in your problem set. And this is a conceptual problem that I would like you to try. Okay. So let's go ahead and let's take about uh, 2 or 3 minutes, 2 or 3 minutes to work through this problem here. So on the screen right here, let's go ahead and let's work through this problem. Take about 2 or 3 minutes to work out this problem, and then please make sure you offer an explanation for your answer. Okay, and then we'll talk about it. Okay, so this is a conceptual problem that you need to be able to work through. This is a problem that I came up with. This is a problem that I used. I haven't seen the problem like this on the AP exam, but I can imagine that they would ask you a similar type of question. So go ahead, take about 2 or 3 minutes, and write out. Tell me what the answer is going to be. Will Ka be greater than 1, less than 1, or equal to 1? And then go ahead and explain how you got your answer. Okay, about 3 minutes to get that done. Okay, let's take a look at this problem here. So I'm going to go ahead then, and I'm going to pull up my whiteboard here, and let's work this out. Okay, let's work this out together. Okay, so let me go ahead and expand the whiteboard there. All right, so we're looking at two, and you'll need, and again, I think you'll need to go back to, I think it's table 14.2. You'll need to go to table 14.2 to get the Ka values to get this problem done. So I'm sorry, they give you the Ka values. Sorry, they give you the Ka values. And so let's go ahead and let's take a look at what's happening. The equation that they're asking you about, the reaction that they're asking you about, is this reaction, or the reaction that they're asking you about is not an acid-base reaction. The reaction involves hydrocyanic acid. Okay? I'm sorry, it's not an acid dissociation problem. It's not asking about acid dissociation, but it's asking about the reaction between an acid and a base. Okay, so let's go ahead and let's write this out here. Okay? And we have then HF, hydrogen fluoride, hydrofluoric acid, and cyanide. Okay, so let's go ahead then and let's identify the acid and base first. So hopefully in this reaction, then you'll notice then that the acid is here. So this is acid. This is a base right here. How do we know that this is going to be a base? Because in this reaction then, to form this, it is the fluoride ion here that picks up the hydrogen from the hydrocyanic acid to form then hydrofluoric acid. Therefore, this is going to be your conjugate acid. Okay, and this will be your conjugate base. Okay, so that's what we have here. Okay, and then what they do then is they give us, so this is not acid dissociation, but what they do give us is that they do give us the Ka. So they give us the Ka for hydrocyanic acid. Okay, so what they're giving us is the Ka for this process right here. Okay, the Ka is not for this reaction. The Kas that they give us is not the equilibrium constant for this reaction. Please make sure you keep that in mind. This reaction here has its own equilibrium constant, which we do not know about yet. We don't know this equilibrium constant yet. So the equilibrium constant for this reaction are not the Ka values that you were given here. So the Ka values that you're given here refers to the process in which these compounds, these acids, dissociate. So the Ka for this one is 6.2 times 10 to the minus 10. Okay. All right. So, and then they give us the Ka for the hydrofluoric acid. So let's go ahead and write that down, which gives us hydrogen ions and fluoride ions. And the Ka for this this process is 7.2 times 10 to the minus 4. Okay. All right. So what does this tell us so far? It tells us that if we look at the Ka values, they tell us then that hydrofluoric acid is a much stronger acid. It's a much stronger acid, which means then the equilibrium will favor the right-hand side here. Okay? However, if you on the other side of things, if you take a look at hydrocyanic acid, I'm going to go ahead. Actually, let me go ahead and write this here. Okay, so when we take a look at the Ka values, it tells us then that the process here favors the products. Okay, whereas with the hydrocyanic acid, if we look at its Ka, which is very small, okay, we can essentially see the reverse, where the equilibrium favors the products, the reactant side, okay, the undissociated acid. Okay, so between these two here, then hydrocyanic acid, HCN, is the weaker of the two acids. It will dissociate. It will form hydrogen ions and the cyanide. It has to, or else it's not an acid, but it doesn't do so as well as hydrofluoric acid. So that's your starting point. That's what you need to make sure you understand. Okay. So the reason why they give us these two, okay, and make sure you understand this, the reason why they give us these two is that based on these two Ka values, we can determine then the direction, which side of the reaction here will equilibrium favor. Okay? And based on that, we can then determine then whether the K for this equilibrium constant for this value is going to be large or small. Okay. All right. So let's go ahead and write out the law of mass action. Let's go ahead and let's work this out. Okay. Let's write out the law of mass action for this reaction here. Okay, so let's go ahead and write that out. K for this reaction then is going to be the concentration of hydrofluoric acid over the concentration of cyanide ions, okay, all over the concentration of hydrogen cyanide over the concentration of fluoride ions. Okay? All right. So with that said, if you take a look at this, what we are saying here, based on our Ka values, and hydrofluoric acid here is more willing to give up its light. It wants to dissociate. Okay? And on top of that, because if we take a look at the hydrocyanic acid, because the reaction favors the right, the cyanide ion wants to give up its electron. So therefore, this base here, this is a fairly strong base. This is a stronger base. This is a strong base Okay, this is a weak base. Okay, this is a weak acid. Okay, this is a strong acid, stronger acid. I should say that between the two, that's a strong. Okay, so what that means then is that as a strong acid, hydrofluoric acid, HF, wants to do this. It wants to donate its hydrogen ion. As a strong base, the cyanide ion wants to pick up a hydrogen ion. Where do you think it's going to get the hydrogen ion from? It's going to get it from the hydrofluoric acid. So if we go back to our original equation here, what happens then is this reaction will favor the left-hand side. The reaction here, the cyanide picking up the hydrogen ion from hydrofluoric acid, is a better process than the fluoride ion, which is a weak base, trying to pick up a hydrogen from the hydrocyanic acid. So understand, as a weak acid, hydrocyanic acid does not want to dissociate. It doesn't want to give up its hydrogen ion. It's reluctant to donate its hydrogen ion. Okay? As a weak base, the fluoride ion doesn't want to take a hydrogen ion. Okay, so that means the two, when they are paired up here, they don't want to exchange the hydrogen ion. Whereas these two, where we see then that HF, hydrofluoric acid, is a strong acid. It wants to give up its hydrogen. It wants to donate. It wants to give up its hydrogen ion. And so when it finds the cyanide ion, which is a strong base, and as a strong base, it wants to pick up a hydrogen. Then we see then that the process here, and if we take a look at this, and now we can write the arrows. Okay, the process here will favor going towards the left, much more so than the right. Okay, that means then these two will do a better job of exchanging hydrogen ions to form these two here. And so equilibrium will favor the left-hand side, will favor the reactants. And we said then that, so then obviously if it favors left-hand side, K cannot be equal to 1. Okay? Now for K to be greater than 1, we have to have more product here than reactants. Okay, and we don't have that. Okay, remember the reaction is moving towards the left. Okay, so K can't be greater than 1. K has to be less than 1 because we'll end up at equilibrium. We'll have more reactant than product. Okay, and so our answer then, with that said, K will be, K is going to be less than 1. So our answer is K is going to be less than 1. Okay. All right. Hopefully you were able to get that. Okay, so it starts then right at the reaction. Okay, make sure you're able to do that right at the reaction. Understand what the Ka values, or what you're supposed to use them for. Understand then this equilibrium here. The Ka values here will help you understand this equilibrium here. Okay, and once you have the law of mass action written, you can go ahead at that point then see then that since we're not going to be, K can't be equal to 1. For K to be equal to 1, you'll have to have the same amount of reactant to product at equilibrium. And the only way we can have that is if the Ka's here are the same. Okay, so that's not going to be the case. If K is going to be greater than 1, we should end up with more product here. The numerator should be larger. That means we should have more product, okay? Which we don't, because hydrocyanic acid is a weak acid. Fluoride ion is a weak base. Okay, so therefore the reaction won't. These two will not exchange hydrogen ion to shift the reaction towards the right. So you don't see that happening. Therefore, K cannot be greater than 1. Okay, and so with that said, then since hydrofluoric acid is the stronger of the two acids, cyanide is the stronger of the two bases, we will see then the reaction shifting back towards the left at equilibrium. Okay, and so therefore you'll have more reactant than product, and so the denominator will be larger, and so K then will be less than 1. Okay, all right, so hopefully you have that. Okay, what I'd like to do then is let's take a look. So now that we know that K is going to be less than 1, let's take a look at number 8. Okay, so look at number 8 in your problem set, and now what they want you to do is, using what information we have here, they want you to solve for this K. They want you to solve for what K is. We know K is going to be less than 1. What is K then? Okay, so let me go ahead and do this here. Let me go ahead and write this down. This is number 7 in your problem set. Let me ask you then, take a couple minutes, actually take about, whoops, sorry, let me do this here. take about 3 minutes, you guys, and do number 8 in your problem. So do number 8, calculate for Ka, I'm sorry, calculate for the equilibrium constant for this reaction here, okay, using these Ka values. Okay, go ahead and get that done, and let's see what you get. Okay, so take about 3 minutes to get this done. Okay, okay, let's go ahead and let's work this out. Okay, let's take a look at what we have here. Okay, so we have the law of mass action right here for this reaction. We have it written there already. Okay, so we have it written there, and so therefore then we need to determine then, and the problem here is that we're not given any concentrations. How are we supposed to solve for the equilibrium constant for this reaction if we're not given any concentrations? All right. Well, we are given Ka's here. We are given Ka's here. Now, let's take a look at what we have right here. Okay. And let me go ahead and write out the law of mass action for each one of these. Okay, so let's write out the law of mass action for hydrocyanic acid and the Ka there. Okay, so the Ka for hydrocyanic acid, let's go ahead and write that down. Okay, so the Ka for that one is going to be then the concentration of hydrogen ions over the concentration of cyanide ions all over the concentration of the undissociated acid, HCN. Okay. Again, we're leaving out water here. Remember, guys, because water is a liquid. So remember, water is present here, but we're leaving that out because water is pure liquid. Okay. All right. So that's the K. That's how we get Ka. Ka then is the equilibrium constant for the acid dissociation. That's the law of mass action for the Ka value for hydrocyanic acid, HCN. Let's do the same thing for hydrofluoric acid. Okay. In order to get the, let's write out the law of mass action of the hydrofluoric acid. It's going to be the hydrogen ion times the fluoride ion concentration all over the hydrofluoric ion concentration. Now, number 8 looks difficult. Okay, number 8 looks difficult, but if you take a look at this, then it's basically just algebra, folks. Okay, it's basically just algebra, because let's take a look at what we have here. Okay. So if you take a look at this here, we have then take a look at these three equilibrium constant expressions here. This one right here, let's take a look at, I'm going to highlight this really quickly. Okay. Let's take a look at number 1, this equation, this equation, and this equation. Let's take a look at those 3. Look at how they're related. Look at how they're related. If you take a look at this here, we have HF, hydrofluoric acid in the numerator, and the cyanide ion in the numerator as well. We have cyanide ion in the numerator here, but hydrofluoric acid in the denominator here. Okay, be careful about that. Okay, looking at the denominator here for the first equation. Okay, we have hydrocyanic acid, HCN, in the denominator and fluoride ions in the denominator. Looking at this equation here, HCN is in the denominator. Okay, however, fluoride ions here is in the numerator. Okay, so what can we do? Well, can you see then that if we can combine these two reactions, these two equations together, if we can combine them together, we can make this, but we can't combine them in this way here. Okay, we cannot combine them in this way here. Let's imagine if we take the reciprocal of this. Okay, that means then let's take the reciprocal, which is 1 over Ka. Let's take the reciprocal of that. Okay. So let's go ahead and rewrite this equation here to get the reciprocal. Okay, let's go ahead and rewrite this equation. So we're going to write the expression of 1 over Ka for this here. So that means then that's going to be equal to HF over hydrogen ion times fluoride ions. All right. Look at that right there, folks. Okay. So now we need to get to this equation here. To get to this equation here, we needed fluoride in the denominator. By taking the reciprocal of the Ka for this equation, that's taking the reciprocal, we now have fluoride in the denominator. Furthermore, we have, by doing that, we have placed HF in the numerator, and which is what we have here. So right now, we have 2 separate equations. We have 2 separate equations here. So how would we combine them together? Okay, how would we combine them together to get this? Okay, so let's take a look at that. Okay. So can you see then, to get this value here, can you see then that we multiply this value for Ka, okay, So let's go ahead and do that. So we're going to take H plus times Cn minus all over HCN, and we multiply that by this right here, that expression right here, which is going to give us HF over hydrogen ion concentration times F minus. Okay. If we multiply those together, look what happens, you guys. The hydrogen ion cancels out. And what are we left with? We are left with HF in the numerator, Cn in the numerator, HCN in the denominator, and F minus in the denominator. By multiplying this expression here, by multiplying this value right here, by multiplying the reciprocal of the Ka for hydrofluoric acid times the Ka, the law of mass action for hydrocyanic acid, we get the equilibrium expression for this reaction here. That's what we have right here. So how do we solve for K then? Because we need a numerical value. Well, let's consider what we have here, folks. Okay, we have here then, let's work this out. K then is going to be equal to taking the Ka value for HCN, and I'll write this down as HCN. We need the K value for HCN. That's what we have right here. And we're going to multiply that by the reciprocal of the Ka value for HF. Do you see that? Remember, this is the reciprocal for this is the reciprocal of the Ka for hydrofluoric acid. And so solving for this then, folks, we take then the Ka value for cyanide, which is going to be 6.2 times 10 to the minus 10. Okay. And we're going to multiply that by the reciprocal of the K value for HF, which is going to be 7.2 times 10 to the minus 4. And that is how we would get the value, equilibrium constant, for this reaction right here. And that, and hopefully if you punch it in your calculator, you would get that 8.6 times 10 to the minus 7. And that is our answer for number 8. Okay. So a little bit of calculation that requires that you do understand how the, so I think here, folks, the chemistry is recognizing what the Ka values are, what these Ka values are, and finding these. The chemistry is writing out the law of mass action for these three processes, for this equilibrium here, for this equilibrium, and for this equilibrium. That's what equation 1, 2, and 3 are supposed to represent. Okay, that's the chemistry. After the chemistry, it's more logic, a little bit of logic, and a little bit of math, and that's it. So this problem ends up being very simple. It looks very difficult on the surface of it because we're trying to find a value, a numerical value for this equilibrium concentration here. I'm sorry, for this equilibrium reaction here, and yet we're not given any concentration value. Okay? We don't need it. We don't need it, as long as you understand what these Ka values should represent. Okay? All right, very good, you guys, very good. Okay, so let me go ahead and save that for you. All right, so please make sure you you get the homework done. So set C will give you a chance to practice this some more, but we do have to continue on. Okay, let's continue on then. And let's take a look at what we have here. Okay, so whoops, let me go do this. All right, so I'm sorry, we already got this. That's less than 1 K is less than 1. We solved for that one already. That's 8.6 times 10 to the minus 7. All right. So what we're going to do then is I'm going to quickly talk about the value for what pHs are for with you. I want to talk about that, and then hopefully this will go fairly quickly. Okay, so when we talk about pHs, the pH scale is a way that we can determine then the concentration of hydrogen ions in a solution. And so the pH scale is a way that we can determine the concentration, not the strength, but the concentration of an acid, and how concentrated the acid is. Now, why do we use pH? Because if you notice with the hydrogen ion concentrations for most of the acids, the hydrogen ion concentration ends up being fairly small. It ends up being a number much less than 1. And so what the pH scale does, what the pH calculation does for us is it converts that very small number into a number that is greater than 1. Okay, greater than 1. So the pH scale then, the pH then is the calculation of the pH is a very straightforward calculation. It's just taking the hydrogen ion concentration and taking the negative log of that. Okay, because these numbers tend to be less than 1. If you only take the log of the hydrogen ion concentration, end up with a negative number. So we don't want that. So we take the negative of that particular log, and that way then we end up with a positive number, which gives us then a scale that ranges from 1 to about 14. 1 to about 14. Occasionally you will see pH is less than 1. That won't happen very often. And occasionally you'll see a pH that's greater than 14. That doesn't happen very often either. Okay? And so with that said then, the scale ranges to the pH scale. So once you calculate for it, the pH scale ranges from on the order of pH of 1 all the way through 14. Okay, so the pH scale ranges from 1 to 14. Okay. It's a way that we can measure the acidity of or measure the acidity of a particular solution. We have instruments that measure pH. We have a pH meter, and unfortunately, we may until we are back in school, we won't be able to use that. But we have pH paper. But the pH meter actually gives us a reading. It gives us a pH reading, which we then can convert to the hydrogen ion concentration using the inverse log here. Okay? But if we have the hydrogen ion concentration, we can calculate for the pH. Okay. All right. So with that said, with this calculation, I think the only difficult part of this calculation is going to involve significant figures here. And I want to highlight this part for you because this is an odd way to determine significant figures. Okay, so this is where you have to practice a little bit. Okay, the calculation for the pH is very simple, you guys. The calculation for the pH is simple. You just have to make sure then that you understand that sig figs for the pH is a little bit odd, so you got to be careful with that. Okay, so this is how we determine significant figures for once we get it. Okay, so the number of decimal places in the log. Okay, so the number of decimal places once we get that is going to be equal to the number of significant figures in our original number. And just keep that in mind. It looks a little bit odd, but I'll help you through it. Okay, and then as we work through this one, you'll see this. Okay, so the pH, the sig figs in our pH, the number of decimal places that we're allowed to keep for the pH. Okay, the number of decimal places that we're allowed to keep for the pH is going to be equal to the number of significant figures in the hydrogen ion concentration. Okay, so that's what you need to keep in mind. So the number of decimal places for the pH, let me go ahead and write that. So number of decimal places, so the pH decimal places is going to correspond to the number of significant figures for the hydrogen ion concentration. Okay. So kind of keep this in mind a little bit here. So keep this general rule here in mind, and that should help you. So the pH, the decimal place, not the significant figures for the decimal place, but the for the pH, but the number of decimal places you're allowed to keep is going to be dependent on the number of significant figures in the hydrogen ion concentration. Okay, so keep that in mind as we move forward with this. Okay. All right, let's go ahead then and let's continue on. And let's take a look at what we have here. Okay. All right, so with that said, then, like I said, the pH scale ranges from about 1 to about 14 here. Occasionally, like I said, you'll rarely ever see 0, and you'll rarely ever see anything less than 1, and rarely you'll see anything less than 14. But the pH scale is going to range from 14 at the largest, so you have 14 at the top, and then roughly 0 at the bottom in theory. But like I said, but typically you won't see anything less than that. Okay. Hydrochloric acid then is there, but like I said, typically you'll see it in here. Okay. All right. So with that said, then anything greater. So if we take a look at this, anything greater. So there's the cutoff point here. I'm sorry. Let me go and do this first. pH of 7 then represents then neutral. Okay, neutral, which gives us a hydrogen ion concentration of 10 to the minus 7. So this is neutral here. So this is an important important mark on the pH scale here, okay? Because anything that's greater than 7 is going to be basic. Okay? Anything greater than 7 is going to be basic. Anything less than 7 is going to be acidic. So a pH of less than 7 is going to be acidic. A pH greater than 7 will be basic. A pH of 7 will be neutral. Will just be neutral. Okay? So you want to make sure you keep that in mind as we go through this. Okay? All right, let's go ahead then. And let's calculate. Let's practice this a little bit. Okay. All right. So we have then a pH here. We were given a hydrogen ion concentration. Let's go ahead and take a look at this. The hydrogen ion concentration here. We were told then. Whoa, let me go here. The hydrogen ion concentration is we're told it's 1 times 10 to the minus 4. Okay. So the hydrogen ion concentration here is equal to 1.0 times 10 to the minus 4 molar. Okay. Real quick, the pH again is the negative log of that hydrogen ion concentration. Okay. All right, so it's plug and chug at this point, folks. Okay, so the pH then is going to be the negative log. Punching this into your calculator. Actually, you probably don't have to punch it in. Most of you can do this in your head. With the negative log of 1 times 10 to the minus 4. Okay. Okay. So therefore, that if you take the log of 1 to 10 to the minus 4, that's going to be a negative 4. So you got to take the negative of that. The pH then here is going to be 4. Okay. All right. Don't stop there. So let's practice. Let's practice our significant figure rules now. Okay. All right. So in the hydrogen ion concentration here. Okay. If you take a look at this, this number has 2 significant figures. Okay. Our answer then has to have 2 decimal places included in there. So the pH here, so our final answer has to be 4.00, not just 4, 4.00. Because you have 2 significant figures here, we have to end up with an answer in which we have 2 decimal places. We have to have those 2 decimal places in our pH. Okay, so our answer ends up being 4. The pH then has 3 significant figures. It has 3 significant figures, but it's these 2 decimal places here that we use that come from these 2 significant figures here. Okay, so make sure you keep that in mind. Okay, all right. So let's go ahead then. Let's take a look at the next one. Let's take a look at the next one. So I'm going to go ahead and highlight this because this is what we're going to use. So this is the equation you're going to use. Okay, all right. So for the second one, if you notice here, they don't give us the hydrogen ion concentration. They give us the hydroxide ion concentration. Okay, so here they give us the OH minus. They give us the hydroxide ion concentration of 0.04 molar. Okay, so that's the hydroxide ion concentration. The pH is the negative log of the hydrogen ion concentration. So how do we get the hydrogen ion concentration? Okay. Well, remember, we have a way. It's going to be Kw divided by the hydroxide ion concentration. That's why we had to learn about Kw. So substituting that in, it's going to be 1 times 10 to the minus 14 all over 0.040. Okay. And so that gives us a value of 2.5 times 10 to the minus 13 molar. Okay, so that's the hydrogen ion concentration. Now we can go ahead and take the pH. Now that we have the hydrogen ion concentration, we go ahead and calculate for the pH, which is going to be then the negative log of this number here, not of this number. So be careful about that. 2.5 times 10 to the minus 13. Board's acting up again. It was being, oh, there it is. It was being good before. 10 to the minus 13. Okay, molar. Okay, and so the pH, let me go into this. Okay. All right, so you plug that into your calculator. Make sure you are able to find the log button, you guys. Make sure then that you can use scientific notation. Okay, so the pH here then, now, let's consider what we have here. Okay, so once you punch it in your calculator, okay, we got to figure out how many decimal places we're allowed to keep here. Okay, so we have 2 significant figures in our original concentration there, okay, which means then we have to carry 2 decimal places. We have to carry 2 decimal places in our final answer. Okay, so therefore we have to write this out as 12 5.60. So therefore, we have to have 2 decimal places right here. Okay. So there are 2 decimal places. As a result of these 2 significant figures here, we should have 2 decimal places. But if you notice, then our final answer has 4. Oh, sorry, our final answer should have 4 significant figures. Because of those 2 decimal places, our final answer then should have 4 significant figures. Okay. All right. All right, very good. Practice this. So that's why for set C, you guys, it's not so much doing this calculation. The pH should be very simple. The pH should be very simple. It's plug and chug. However, if you're not given the pH, then please if you're given the hydroxide ion concentration, make sure you're able to work out and solve for the hydrogen ion concentration, because that's what you need. You need hydrogen ion concentration. You need H plus, not OH minus. So if you're given OH minus, if you're given the hydroxide ion concentration, you have to solve for the hydrogen ion concentration before you calculate for the pH. Okay, so that's the only extra calculation that you have to do. All right, so with that said then, let me go ahead and ask you, let's take a look at number 9. So these calculations end up being very simple, you guys. Let's take a look at number 9, and let me give you, there we are, answers right there. Let's take a look at number 9. All right, so what I would like you to work this out. Okay, I'd like you to work this out. Take about 2 minutes to work out this problem here. Understand, this time they give you the pH. They give you the pH, and they ask you to find the hydrogen ion concentration in order to get that done. Okay, so go ahead, take about 2 minutes on your paper. Show me how you would find the hydrogen ion concentration of a solution with a pH of 5.85. Okay, so 2 minutes. Okay, let's take a look at this. So we know then that the pH of a solution is going to be equal to the negative log of the hydrogen ion concentration. Okay, so the negative log of the hydrogen ion concentration. So what we need to do then is hopefully, let your calculator do the work, you guys. Let your calculator do the work. I'm not going to, you need to make sure you check your calculator and learn how to use the inverse log function here. Okay. All right, so here they give you the pH. So let's go ahead then and let's write this out. So the negative log, okay, the negative log, so we have the negative log of the hydrogen ion concentration is now going to be equal to 5.85. Okay, so doing the log of the hydrogen ion concentration of negative 5.85. Now, what you're going to have to do is you're going to either it's going to be the inverse log. Usually the inverse log is going to be a second function key on many of these calculators here. So on my TI-84, we have it as a second function, but you'll see it as 10 to the x. You'll see it as inverse log, then older calculators. But again, it would be a second function key. But that's what you have to do. Okay, you have to take basically what you're doing is you're dividing by the log, if you want to think about it that way. Okay? You're dividing by the log in order to get the hydrogen ion concentration. Okay? So which means then, to get the hydrogen ion concentration, you're going to be basically raising 10, since 10 to the x is say 5, negative 5.85. So make sure you keep that in mind. It has to be negative 5.85. And then if you punch that into your calculator, let me go ahead and do that real quick for us. Okay, just to have you take a look at that inverse second function log. Oops, sorry. Negative. Sorry, you guys. Let me go and do this again. There it is. Okay, I get a value that is 1.41253754 times 10 to the minus 6. Okay. All right. We're not allowed to keep all those significant figures. We're not allowed to keep all those significant figures. So to figure out then how many of these digits we're allowed to keep, let's look back at our rule here. Okay. So Remember, the number of decimal places here was determined initially by the number of significant figures in our concentration. Okay, therefore, then we're only allowed to keep 2 significant figures here for our final answer. Okay, so we have 2 decimal places here. Because we have 2 decimal places here, we're only allowed to carry 2 significant figures in our hydrogen ion concentration. And so therefore, our final answer is going to be 1.4 times 10 to the minus 6 molar. That is our final answer for this particular problem. Okay, so with that said then, finding the pH, finding the hydrogen ion concentration should be a fairly straightforward process. Okay. Let's go ahead then, and let me go ahead and save that screen right there. Okay. Let's do, okay. So if you have questions, please make sure you work on set C and then email me your questions. Okay? But we saw an example of a problem previously where we were given the hydroxide ion concentration. We had to find the hydrogen ion concentration before we find the pH. Okay? Now there is a quicker and simpler way around this. Okay? There is a quicker and simpler way around this. Whoops, okay, and that is if we remember this here. Okay, so I'm going to work this out. Show you this here. We know then to find the water dissociation constant, okay, which is going to be equal to 10 to the minus 14 here. Remember, I'm going to go ahead and write this here. That's going to be equal to 1 times 10 to the minus 14. Okay. Now, if you notice what I do here next is I take the negative log of both sides. So negative log of Kw, negative log of hydrogen ion concentration, negative log of the hydroxide ion concentration here as well. Okay. So with that said then, what you're going to notice then is we already know what this is. The negative log of hydrogen ion concentration is our pH. There it is right there. The negative log of Kw gives us what we call pKw, and the negative log of the hydroxide ion concentration gives us what we call POH. So if you want to think about it, the letter P right here, whenever we see that letter P, we can think of it as an operator, an operator that tells us to do a particular operation. Okay, whoops, sorry. Okay, so whenever you see that letter P, at least in the context of our chemistry here, whenever you see that letter P in the context of our chemistry, it is an operator that tells us to take the negative log of anything that follows it. Okay, so when you ever see that letter P there, it is telling you the operation you have to do is to take the negative log of whatever follows it. Okay, so if in order to get that, so P of OH means that we take the negative log of the hydroxide ion concentration. P of H, which means then take the negative log of the hydrogen ion concentration. pKw, negative log of the Kw. You're going to see, for example, pKa when we work through this, as we go through this. And so what does pKa mean then? We have to take the negative log of the Ka value. And you're going to see that as well. You'll see then pKb, which means then we're going to take the negative log of Kb. And what is Kb? Kb is the equilibrium constant for the base dissociation. We'll talk about that a little bit more. Hopefully, if not tomorrow, we'll talk about it on Monday, the last video, and then I'll see you on Tuesday. Okay. All right. So P then is an operator. So it's an operator that tells you specifically to take the negative log of whatever follows it. And so therefore, since we know what the negative pKw is, we can get this very useful equation right here. This very useful equation right here, which will allow us to find POH, okay, or the pH, okay, if we know the other one. So with that said, then what we could have done with the problem that I gave you before, we could have solved for the POH, okay, by taking the negative log of the hydroxide ion concentration that we were given, plug it into this equation here, and then we can find the pH. Okay? So this equation here, you guys, will end up being very useful, and it will save you a whole lot of time. So make sure you remember this one. They on the AP exam, they don't actually give you this equation, and so you're gonna have to make sure you remember it. Okay. Okay. So let's go ahead then. Let's apply it. Let's apply it and let's take a look at it. Okay. Okay. Let's work out this problem here. Let's work out these two problems together. We're running a little low on time, so I'm going to work these out for you. Okay, so we want to find the POH. So in this particular problem here, we're trying to find the POH of both of these solutions here. So in the very first one, we were given the hydrogen ion concentration. we're given the hydrogen ion concentration of 1 times 10 to the minus 4 molar. And they want us to find the pOH. Okay. Now, with that said, what we can do here is we can find the pH. So find the pH here, which is going to be the negative log of the hydrogen ion concentration, which is 1.0 times 10 to the minus 4 molar, which gives us a value of 4. That's going to be our pH. Okay? And so to find the pOH then, and remember the equation that I just taught you, that I just introduced you to, is going to be pH plus pOH is going to be equal to 14. Okay? And that means then to solve for the pOH, you guys, let's go ahead and let's plug this in. Again, the math ends up being ridiculously simple here, you guys. So let's go ahead then, and with that said, let me go ahead and, okay. All right, so with that said then, to find then the pOH, it's going to be 14 minus the pH, 14 minus 4, and so therefore the pOH is going to be 10. However, now don't stop here. We can't leave it at 10. The significant figures then are going to be off here. Okay, so let's go ahead and consider what we have here. We have 2 significant figures here, which means that we need 2 decimal places here. That means we have to add in 2 more zeros. So in order to get this, our final answer has to have 4 significant figures. So we need those 2 decimal places. So 10.00. Okay. All right. So that's for the first one. Let's go ahead and let's take a look at the second calculation. Okay. So here, this time we were given the hydroxide ion concentration. Okay, already. So that's going to be 0.040 molar. That's our hydroxide ion concentration. So define the pOH, you guys. Again, the pOH, remember, I already showed you this. To get the pOH, the P is basically telling us to take the negative log of whatever follows it, which is going to be the hydroxide ion concentration. To define the pOH, then, okay, we just need to get the negative log of the hydroxide ion concentration, which is going to be 0.040 molar. Okay. Plugging that in then, and then making sure then that we have the correct number of decimal places. If we have 2 significant figures here, okay, our final answer then must have 2 decimal places, which is going to give us 1.40. There's the 2 decimal places. This gives us a total of 3 significant figures. Okay. All right. pH, please practice the pH, you guys. We're gonna I'll pick up with this discussion tomorrow as well. And I know it's New Year's, but we got to try to get it covered. And so I'll post a video for you for tomorrow's video. Then we'll practice a little bit more doing these pH calculations, these pOH calculations, and then I'm going to start into equilibrium, acid-base equilibrium calculations, and we'll start on that hopefully on Monday. And then by the time I see you on Tuesday, we'll pick up with that. Okay. All right. Have a good rest of your day, folks. Have a good and safe New Year's Eve, and I will see you tomorrow in the new year. Okay. Have a good day, folks. I'll see you.